Hi, good afternoon, good morning, good evening. Welcome to SETI Live. My name is Simon Steele. I'm the Deputy Director of the Carl Sagan Center at the SETI Institute here in Mountain View, California. And I have great pleasure in welcoming Melissa McClure from Leiden University, all the way over in Holland. So it's later on in the day for you, Melissa, isn't it?
Yeah, it's actually
Yes.
dark outside, which is why it
Okay.
looks like I'm in a cave right now.
Is it raining or is it nice out?
It's just completely night.
Okay, yeah. So Melissa and her team have made this fascinating discovery. If we run the clocks back a little bit, about 5 billion years, of course, our sun and the family of planets were born out of a condensing ball of gas and dust. The Proto-Stellar formed, and then the planets started forming. Now, this process, although we know a lot about it in theory, has not been witnessed directly. This very beginning of this process. And Melissa and her team have actually seen a star produce its planets, or at least the start of the planets, for the first time ever. And this result has just been published in Nature, and it will tell us a lot about the origins of our solar system, as well as the origin of all other solar systems in our galaxy. Melissa, can you set the scene? Did you go out to discover a solar system being born?
So this actually wasn't what we were necessarily intending to discover with this particular data set. So this data, the JWST portion was originally designed to study how ices in the sort of collapsing ball of dust and gas that ends up forming the protostar around which you have a disk form and the planets form in that, how these ices end up getting thermally processed or heated up and then partially destroyed during this infall stage. And this was important because these ices could go on to form ices on comets, which then are thought to have brought water to the surface of Earth eventually in our solar system. But in this data, we actually had planned for to have one or two sources that we knew were going to be really hot, because we knew that they had these sort of crystalline minerals that indicate that rocks have been heated up quite a bit. And when we got this data, we saw not only were these crystalline minerals that we suspected were there, they were definitely there, but we also had evidence that they had been completely vaporized into silicon monoxide gas, which is one of the things that happens when you burn up rocks. And that was a very clear indication that we were observing this very hot early moment around this newborn protostar, where we think that the materials that condensed out of that go on to form small particles that are about the size of pebbles that we end up seeing in solar system meteorites. And these types of sort of 1 centimeter size inclusions in meteorites are actually what is used to age date the solar system. So they're sort of the T equals 0 moment because of the oldest things we see in the solar system.
Right. So we are looking at, as you say, the time zero, the starting point of planet formation here.
Exactly.
Yes. So this set the scene here. Where is this up now? This object is called HOPS 315, which is a wonderful name.
Yeah, it stands for Herschel Orion Protostar Survey. So it was a survey that was done of the Orion molecular cloud, which is where this particular protostar is located.
Right, and this is a huge cloud
really
of gas and dust, and I think it's part of the Orion Nebula, isn't it? Or the Orion Nebula is part of this. This is a giant cloud.
Exactly. So there's several hundred protostars spread all across the Orion Nebula, and it can be broken down into different subclouds. This particular protostar is in sort of a cluster where there's maybe like 30 to 40 other protostars along with it. But it's the only one that shows these crystalline features and the only one that shows this SiO gas.
Yeah. Is it the only one? I mean, we can come back. This is going into more detail at the moment, but is it the only one because it's a it's the only one at that particular stage in its evolution, or is it just nicely lined up for us?
So we think it's nicely lined up for us, because if you could we actually see at the ALMA image for a moment? So exactly. So this is a very high resolution image with ALMA that we actually my colleague Meryl van 't Hoff, who's a professor at Purdue, applied for this ALMA time, and basically you can see that this protostar, the protostar itself is located where there's like a sort of dark dot at the very center of the image, and you can see there's like an hourglass shape that's coming out from it, and that's this outflow of material that's been blasting out away from the star. And then there's a narrower line sort of up the center on the diagonal, and that's a jet in this system. And normally, if you were looking at a protostar and it would have a somewhat narrower outflow. So instead of being wide open like an hourglass, it might look more like like a champagne flute versus like a wine glass sort of. So this is more like a wine glass, and normally they would look like champagne flutes. And because of that, you have the jet in the center. There's not much space for you to actually observe between the edge of the glass and the jet going down the center. But in this case, because you have the wine glass shape instead, it has enough space that you can actually observe in between the outflow cavity wall and the jet down to where the protostar is forming at its very center. Okay, so it's a very special inclination.
Yeah. So we're going to dig deep into this image in a second, because A, it's beautiful, and B, there's so much information there. But just to remind people, if you are tuning in, let us know where you are tuning in from. We've got quite a few here from David from Halifax, Nova Scotia. We've got people tuning in from Greece. We've got Ruud is calling in from the Netherlands, Jess from Northern California rather, and Patricia's from London. So welcome everyone. Thanks for letting us know where you're coming in from. Now, a couple of things. First of all, this is an image from ALMA. You used two very different telescopes to do these observations. Can you say a little bit about ALMA? Because this is not a visible light image, is it? This is a radio image.
Correct. It's a millimeter wavelengths radio image. So it's ALMA is very good at seeing colder dust, and JWST is good at seeing the sort of hot, warm dust that's closer to the protostar. So because we wanted to get sort of like a big picture image, we turned to ALMA to actually sketch out sort of the geometry of the system with this outflow cavity and the jet. And the area that was visible with JWST is actually that very tiny dark spot at the center that the jet is sort of coming down into. Yeah. Much smaller field of view.
Right. So this is a colorized image to allow us to see a picture of radio waves coming out of this. Yes. What's the sort of scale here? And can you say a little bit about jets? Why have we got a star shooting jets out?
Yeah. It seems kind of strange. Yeah. So the scale on this, the center dark area is about roughly the size of our solar system in radius. Mm-hmm. So if that would be like our solar system out to maybe the orbit of Pluto, a little further than that. Mm-hmm. And then if you're thinking like the whole big scale of this thing, it would sort of go all the way out to where you have like the Oort cloud, maybe a little bit larger than that, to give some more familiar frame of reference. Yeah.
So this system is very, very big. I mean, it's almost out. You could say it's sort of halfway to Alpha Centauri if you're looking at it at the sort of scale of our planetary system. Very large. Maybe not that big.
Not quite that big, but okay. but still pretty big.
Yeah.
And you wanted to know about the jet.
Yes. Tell us about a jet. This is a star like the sun, or like the sun was 5 billion years ago, and it's now doing a sort of Death Star thing with shooting jets out of each side. What is happening there?
So this is actually one of the very interesting things about these protostars. You have so the sort of dark area around it is this initial cold ball of gas and dust in the molecular cloud that's collapsed. It's in the process of collapsing.
Mm-hmm.
It's obviously collapsed already to form the protostar at the center. But because the molecular cloud is actually rotating, it's a bit like one of those like ice skaters when they do one of the spins on the ice, and they have their arms really out very far, and they're rotating a little bit slowly, but then they pull their arms in toward their chest, and then they start spinning like really fast, and that's how they can spin for a really long time, right? So this material in the molecular cloud, it's sort of spinning very slowly, but as it falls in closer to the protostar, it starts spinning faster and faster and faster. And in order to form the star but not break up the material that the star is made of, because it's spinning so fast, you actually have to take a small amount of material and throw it back out of the system, sort of very close to the star, but like straight up into this jet. And that's essentially what it's doing here.
Yeah. So we got, this is a very obviously a very large scale image, and ALMA does that very nicely. You have a very picture, the big picture. You say the next job now is to sort of dig into what's happening at the center, and that's where JWST comes in.
Absolutely. Yeah. So if you if we look at the nature cover slide, perhaps. Thank you. So this is like sort of supposed to be an artist representation of the image that you just saw with ALMA, where you have the wide angle outflow in the sort of orangish color, and then the yellow part of the center is the jet, and then this box here, which was not on the cover actually, but it goes. It shows you what JWST saw when we looked at this. In terms of like an actual image, all we saw was just like the sort of 6-point star that JWST has, because it's like a point source. But when you actually look at the spectrum that comes out, at each wavelength, you get a different amount of light depending on the type of dust and gas that you had in between the JWST and the star itself. So in this case, we had this little plot here on the upper right-hand side. You have a feature that's called the silicate feature. We see it in many protostars, also toward molecular clouds. It's really common. But what's unique about this one is that you have these crystalline silicate features here. So in the colored curves at the top, you see there's like a purple curve, a magenta curve, and a sort of lime green curve. Those are 3 different types of minerals that we commonly see in meteorites. And we've, some parts of this image were removed for clarity, but if you add in a couple other components that are colder components, you get this orange line that's matched against the white data. So that's the minerals that we think have formed in this system. And then on the in the white spectrum, there's this part that looks sort of like a hairy mustache. I know that's a weird way to describe it, but it has like a left side, and then it goes up in the center, and then there's like a right side. So that's actually a band of silicon monoxide gas. So this is where if you took the interstellar cold dust and you got it close to the protostar and you heated it up to the point where it totally vaporized, you produce this gas. And then as that gas starts to cool down, then you end up condensing out these colored minerals that we have here. And then what this would actually look like in the solar system, these are the picture at the bottom here, are 2 different types of mineral inclusions that you have sometimes in meteorites. And the one at the right-hand side with the little things that look like crystals, that's what we think is being formed here with these crystalline minerals that we see in the spectrum. Okay.
Now, silicon monoxide is something that we're not that familiar with. Silicon dioxide is something we're very familiar with, which is on the beaches around the world, but silicon monoxide. So why is this so important? What's the role of this?
So it's a very clear signature that the interstellar rocky material that we have has been completely burned up, because it produces silicon monoxide gas when it burns up. Because like you said, silicon dioxide, which is actually this purple curve at the top, that's actually silicon dioxide. That's a component in sand, and it's a component in many other types of silicate minerals that we see in the interstellar medium. So when you thermally disrupt that rocky grain as you're moving it in toward the star, you produce some iron, some magnesium, and some silicon monoxide.
Okay. So, so paint a picture of what it's like here. If we could really zoom in with a very nice, big telescope, what are the conditions looking like as we sort of fly in? Rather a dangerous environment to fly through, probably at the moment.
Definitely, it's really hot.
Yeah.
Maybe this would be a good time to show the cartoon, if that's. So if you were flying in, so we have here, there's a line labeled sight line. So you'd be approaching from like the upper right-hand side. You would see that there's this sort of wide angle outflow cavity that actually interfaces with a disk wind that's blowing material out. And then in between that and this jet that you saw in the system, which is indicated here in blue, you would see that you have a very warm inner disk, but you would see that there's like a glowing hot part at its center, and that's this region here in yellow that's labeled thermostat. But that's just because the region very close to these central protostars is extremely hot. And then you would see probably some of these crystals, some of which are actually silicon dioxide, but also forsterite, which is like the August birthstone peridot. So it's a green color. So you would see like little, like a sort of sea of green pebbles floating around in this surface layer. And then probably the star itself would be quite large and having like some flares from accreting material that's being siphoned from the disk onto the star along these sort of curved lines that connect it to the disk.
So looking at the scale there, this is a log scale, of course, and a radius 1 AU. So that's the distance of the Earth to the Sun, to give us a sense of scale. And then out to 10, that's out to Saturn. So this is a very big scale, isn't it, in terms of and a very big disk. And so this disk presumably is, it's a dynamic environment. Some of this stuff is falling onto the star, some of it is being blown out into the jet, and some of it is going to make planets.
Yeah, it's incredibly dynamic. There's a lot going on. So one of the interesting things that we think from the study is that we were able to identify that the silicon monoxide gas appears to be coming from around 1 AU. Certainly, it's coming from within 2 AU. That's the outer limit that we derived from the ALMA observations of it. But from the JWST observations, we think it's a little closer to 1 AU. But you would have these say interstellar rocky grains that are coming, falling in as you move from the upper right down toward the midplane. They would get hotter and hotter and hotter until they encounter this region around 1200 Kelvin. They would sublimate, releasing the silicon monoxide gas. But because this region has so much movement in it, the gas is really like banging around a lot. It has a lot of turbulence, and we know that hot air rises, right? So this hot silicon monoxide wants to rise up into the atmosphere, and as it does that, it actually starts to cool, and you have these crystalline silicates that condense out of it. But some of those will actually get carried out potentially on a disk wind into the comet-forming region of the disk. Others may actually settle and sink back to the midplane. We think that's what's happening after they form, and then you could start to have them turn into sort of fingernail-sized pebbles. And when you get enough of those pebbles, there are planet formation mechanisms that say that you can trigger an instability in the disk and just like collapse all those pebbles almost semi-instantaneously into a like something like an asteroid sized body.
Okay.
So we could have that, like that's what we think is happening here, where we say pebble trap or planetesimals in the diagram. But we could have the sort of seeds of Earth that are starting to form there.
Yeah. I have to come back to that term instantaneously.
Yeah.
So what's as in cosmic, in sort of the history of the
right.
So what is the time? This is t equals 0. What time scales can you sort of run the clock forward to something that maybe resembles a terrestrial sized planet? What sort of time scales are we running there?
So we know, maybe take just a step back from the meteoritic record in the solar system. We know that after these initial inclusions were formed, then within maybe like 10,000 to 100,000 years, you had the sort of, this is a very technical term, iron meteorite parent bodies, which are basically like the asteroids that formed that were broken apart that then formed iron meteorites, which fell on Earth later. But we know that they're roughly the same age. So within, I think, again, 10,000 to 100,000 years, we should have something that could be like the core of Earth. We think personally, probably this has already happened, because that jet is actually really poor in some metals like iron and magnesium that we might expect to see if you had not formed like these sort of planetary core size bodies. You would expect that all of the dust would move in toward the central star, it would vaporize and then escape in the jet and leave the system. But we don't see this material in the jet, which makes us think that we've already started to form these, asteroid-sized bodies.
Interesting. So the jet is, and there's a question from Terence about what is the jet made of? It's not plasma as such. You're saying it's material. It's sort of stuff that's being thrown out.
Yeah. So it is actually really hot. It's not plasma, but it's just a very hot gas. So the temperature in the jet is somewhere around like 3,000 Kelvin, whereas the temperature in the disk in the region where we see the crystalline silicates is around 500 Kelvin.
Okay. Interesting. Just like to thank Thomas and Shahid for the donations. Thank you very much. We are a non-profit organization, and this helps us keep on air and chatting with people like Melissa. So thank you very much for those donations. This is from a LinkedIn user. This is a protostellar event that mimics our own solar system, and this is quite, the star mass here is very, very similar to a solar mass, isn't it? So we're almost, got a perfect setup here to think about how our solar system began.
Exactly. So right now the star is about the same mass that we think the sun was at this point in its history. So it's around 0.6 solar masses, but it's accreting mass so fast, or eating more mass from the cloud so fast, that it should reach 1 solar mass in the next maybe 1 million years or so. The size of the disk is very similar to what the sun's disk was, sort of like within the orbit of Pluto, more or less. And the mass is very similar to the amount of mass that we think the sun's disk had before the planets formed. So everything is set up here. It should be, we think it's sort of like it's like a solar twin, sort of.
Yeah.
But much younger.
Yeah. Well, we can now watch it develop, and if we keep watching for a few billion years, we'll have to see what happens there. So
yeah. Well, so systems like this are so important because they actually give us like an insight into like being able to observe real-time processes that we think happen in our own solar system, which we can only recover from like sort of partially from the meteoritic record. So I think we're actually looking to discover more sources like this, because it would make an entire class of objects where we could really study these processes in a lot more detail and get insights into how our own terrestrial planets formed, which is really what we want to do.
Yeah, and it's very exciting because we've got a lot of stars out there in our galaxy, and of course, each one of them is a snapshot in time of evolution, isn't it? And
Exactly.
this is very, very important phase. Question from Isatu. What are the limitations here of JWST and ALMA? Are you pushing the limits of these telescopes, and what telescope would you like to get hold of next to follow up?
So this is definitely pushing the limits for ALMA. I think for JWST, this was actually quite a bright source. So it was, sort of low-hanging fruit, so to speak. Like, it was good that we observed it, and it's like, it shows everything that JWST can do, but it was super bright, so we got a lot of detail. For ALMA, we were really at sort of the limit for spatial resolution that ALMA can do, and still measure gas lines at the same time. ALMA can do smaller spatial resolutions if you're observing dust, but that's because dust is really bright because it's hot. I mean, it's cold at ALMA wavelengths, but the dust is much brighter. But for the gas phase lines, there it's really tricky to get much better resolution than we did. So this was really pushing it. There's an upgrade to ALMA that's coming in the next, well, hopefully will be coming like in the next 10 years or so, I think, and that would be really critical for getting better resolution closer in toward these systems. Yeah. And because it would enable you to get these very faint gas lines, but then push it into the full resolution that ALMA can do.
Yeah. Okay. Thank you. So a question from Patricia, and this is about color. Of course, we're dealing with what we call false color at the moment because it's radio. Is all that crystalline stuff really different colors? It's like a jumbled up rainbow. Yes. So what, tell us about the colors that you use, and maybe the colors that are real, if we were observing it with an optical telescope.
Do you mean the colors in the ALMA image, or do you mean the colors that the minerals themselves would be in real life?
That's interesting. Let's talk about the colors of the minerals, because you showed a picture, of what was a cross section of a meteorite, didn't you? Which is quite beautiful.
Yeah. So the image that I showed of the meteorite was actually done, I think, in the X-ray. So again, it's false color imaging, but you can see. So I had mentioned this, that one of the minerals was called forsterite, and this is it's similar to peridot, which is, or it's the same chemical mineral as in peridot, which is a bright green August gemstone, and it's also the same kind of mineral that you have in like the green sand beach in Hawaii and a few other beaches across the world. So it's like a very bright lime green color. The other mineral, enstatite, is like a little bit more smoky and kind of a little bit black, like not quite obsidian, but and then the mineral silica is sort of like a clear, it's glass essentially.
Okay. Yeah, and absolutely beautiful. But and the green sand beach is quite amazing. Having seen it once, it was very, very strange. So actually, to follow on, just talking more about the false colors, when did you choose the color palette for these images, and what's important to you when you do that?
Yeah, so we actually tried a couple different colors at first, and we ended up for the press release images going with this sort of orange color because it went with the cover text of Forged in Fire, so that this is like what it actually looks like with everything on it. But if you had, I think if we'd done anything in not warm colors, it wouldn't really have fit as well with that. And then once we were locked into that color, then blue made a very natural color for the jet, or sort of bluish purple, because it's a high contrast with the orange color.
Okay.
Those are all graphics considerations, not science. But...
Yes. No. Well, it's important, isn't it? Because you want to bring out the contrast, but you also want to give an impression of reality. These are real images. It's just the limitations of our eyes to actually see. Yeah. What next, Melissa? Is this object going to keep your attention for a little while, or are there other exciting things to go off and look at? What is the next step for this research?
Well, right now we're trying to actually find more of them. So we've successfully identified a couple others that we think are like this, and we're writing up one of them right now and applying for more time for some of the others. Once we get that, we'd actually like to see if the types of minerals that you see condensing out vary on an object-to-object basis. And this is partly because, you know, there's in the solar system, there's this idea that if you look at all the different components that you have in meteorites and you make measurements of different isotopes, so like heavy elements or heavy versions of each element, then you look at the pattern that makes, it looks like Earth must have gotten part of its solids from some of these other minerals in the solar system or other bodies in the solar system. But there's still sort of like a missing component that has to get added in order to get the right isotope ratios for Earth. And we think that actually some of these condensates may be some of that missing building block of Earth that the meteoriticists have been looking for. So we're trying to see if we get some objects that are a little bit older than this one and some that are a little bit younger, how do the minerals that we see change, and can we identify the ones that are this missing isotopic building blocks for Earth?
Yeah. Okay. Nice. And one last question, actually, about the process. Now, you know, you're using two, you know, very sophisticated telescopes. You know, one's up in space, one's in Chile. You're in Leiden. You've got lots of collaborators. How do you, you know, what is the admin issues here, putting together such a big team to do this work?
I think the biggest one is actually the time zone differences, because we have people who are based in Europe, in the US, in East Asia, and then if you're trying to have like a telecon to discuss, you know, what you're putting in the paper, you're trying to find a time that works for everybody, and either like someone's always staying up late or waking up really, really early. So I think our record is we had someone who was in Taiwan who was taking some of these calls at like midnight or 1 a.m. and we were like, really just like, let us switch it around, and like we can, you know, get up, you know, stay up late or get up early. you can have it in normal time for once. Yeah. But also putting in telescope proposals, that's really it's very time consuming because the success rates are quite low. So you have to just put in, you know, maybe like 10 proposals if you want to get like 1 or 2 back positively. So you have to put them in over multiple years. And then trying to, if you get time on one telescope, then trying to convince the other telescope that really they should also give you a program to look at the same object on it. That coordination is very difficult.
Yeah. So this is modern science, which is truly global, isn't it?
Yeah. You almost need to have like a degree in management in order just to handle everything.
Well, thank you for, first of all, it's wonderful that you got time on ALMA and JWST, because this is an incredible result. And, you know, seeing a planetary system being born and growing is just such an exciting thing, you know, in watching how the universe evolves, and the story of us, really, as well as the story of this world. Yeah. Thank you very much for joining us, Melissa. Thank you very much, everybody, for tuning in. We are back on the 16th of October. Daniel Whiteson, particle physicist, talking about his upcoming book, Do Aliens Speak Physics? That's going to be an interesting one. Thank you. SETI Institute is a non-profit research center in California. We rely on donations to keep some of our research going and to put on conversations like this. So thank you, everybody, for the donations and for tuning in. And we look forward to seeing you again next time. And thank you again, Melissa. Wonderful to meet you.
Thanks.